So, according to the first law of thermodynamics, internal energy will change as a result of heat flow or work done. For many processes, Q can be calculated as mc delta T, where C is the specific heat capacity. So for isobaric processes, we'd use Cp. For isometric processes, we'd use Cv. And for a solid, there's only one value of the specific heat capacity. Now, it isn't always true that heat flow leads to a temperature change. Exceptions would be, well, number one, if it's an isotherm, because for an isotherm, with there's no change in internal energy, the heat flow is balanced by the work done, and the object doesn't warm up. So that's one case where this doesn't apply. Another case where it doesn't apply is if you're undergoing a phase change, because then there's no change in temperature, and the heat flow is just changing phase, say, from a solid to a liquid. Now, we said that gases have two values, but solids and liquids, like water, just have one value. So here's the specific heat capacity for water. And then there's the latent heat. That's the energy to vaporize a kilogram of water. And then, sorry, that's the latent heat of vaporization. This is the latent heat of fusion. That's the energy required to melt a kilogram of ice. Now, there are four main ways that thermal energy can be transferred into a material, say our thermodynamic working fluid. They can be transferred by conduction, convection, evaporation, and radiation. And we just want to go through the background physics on each of these. We'll start today with a look at conduction. And this, the law of conduction is known as Fourier's law. And it starts with the definition of what's known as thermal resistance. So if we've got some thermal energy that's flowing through this slab of material, you could think of this as, say, perhaps being like a window. And then this is the hot inside of the room, and then that's the cold outside. So obviously there's thermal energy flow through the glass to the outside. The amount of thermal energy flow depends on the thermal resistance of this layer. And the thermal resistance increases as it gets thicker. So it varies directly with the thickness D. And then it varies inversely with the conductivity of the material. So if you're a good conductor, that's a large K, then you have a small resistor. It's a small r. And these are the R values that you'll see displayed on insulation packages. So if you've ever done any, if you've ever bought any fiberglass insulation, you know that R14 is a common value used in the walls of your home. Now, thermal resistances are a lot like electrical resistors. So these two resistances would add together, right? When you stack insulation and wood together, the thermal energy flow here, it's got to flow through both of them. So the total resistance is just the sum of those two. And because flow doesn't appear or disappear, the flow of heat through the first material equals the flow through the second one. So let's see. In electricity, that would be a current. Here, it's going to be heat over time. So I guess instead of charge over time, it's heat over time. So you've got the same amount of thermal energy flow per unit time through both materials. Now, if you have thermal resistors in parallel, then the reciprocal resistances add, just like they do for electrical resistors, and the two thermal energy flows add together. So the total will be the sum of those two flows. So there's a lot of parallels between the flow of heat and the flow of electricity, electric current. Now, that doesn't end when we consider Fourier's law, because what Fourier's law tells us is the rate of flow of thermal energy depends on how big an area that slab has. So you could look at, say, this picture here. So this is the surface area A. And obviously, if you've got more surface area, if you've got a bigger window, then you've got more flow of thermal energy. It varies with the driving force, which is the temperature difference between the outside and inside. And then it varies inversely with the resistance. Okay? Now, this is a lot like Ohm's law, because what we've just said is The flow, which is this one, varies directly with the driving force and inversely with the resistance. Now, for electricity, that was I equals V over R. But for thermal energy, we're saying joules per second of thermal energy is A delta T over the thermal resistance. So there's a lot of similarities there, and that's a helpful analogy for us to keep in mind. So this is Fourier's law of conduction. We'll apply it now to a couple of simple examples. It's easiest if the temperature change is constant. If the delta T is a constant quantity, then this is going to integrate very easily. So here we've got a styrofoam cooler. Okay, so our cooler, and inside our cooler we've got some ice that's melting. So here's a block then. Oops, let's draw it. Not a good color. Come on, you. There we go. Okay, so here's our cooler, styrofoam, and then we've got ice melting on the inside. Now the fact that we're melting ice means that it's 0 C inside and constant. And we're told the room temperature is 20 degrees. So we've got a constant temperature difference of 20 degrees there. So the ice, as it melts, will remain at a constant 0. So that's useful. Now for our surface area, we've actually got 6 sides here to this cooler, and each is 30 by 30. So that's 6 times 0.3 squared, and that'll be in units of square meters. For the thermal resistance, we've got the thickness of the walls divided by the thermal resistance. So the thickness of the walls is 2 inches, so that'll have to be converted to first to centimeters. There's 2.45 centimeters in an inch. And then to meters, we divide by 100. So that's the thickness of the walls. So it's about 5 centimeters, about 0.05 meters. And then the thermal conductivity of the styrofoam is given. It's 0.04 watts per meter Kelvin. And then this is also going to have units of meters, this bit right here. So I'll put it in here maybe. And then, so we're going to get meter squared Kelvin per watt out of this. So the value is 1.27 meter squared Kelvin per watt. Now that's a bit of an awkward unit, but you'll see that it works out nicely. Okay, so we apply Fourier's law. dq dt is A delta T over R. The area, we add up 6 faces, and we get 0.54 meters squared. That's just like adding up 6 flows, because the flow through each side is going to be the same. The temperature gradient is a constant 20 degrees or 20 Kelvin of difference. And then the thermal resistance is the 1.27 meters squared Kelvin per watt. So I said the units work out nicely. So you see the meter squared here just cancels out the area. This Kelvin cancels out the temperature difference. And so we get a rate of flow of thermal energy in watts, joules per second, which is exactly what we expect. We get 8.5 watts of thermal energy flow through the walls of that cooler when it's maintained at a constant 0 inside. Now, if we're going to melt the ice, how much heat is actually required? Well, then we're going to use the latent heat of fusion for water, mass times latent heat of fusion. So let's see, a block of ice, we got 1 kilogram of ice, and it takes 334,000 joules to melt a kilogram. So that tells us how much Q we need. And so we can now solve this equation. Well, dq dt is a constant. So we could just do it the Physics 11 way. Or we could just cross-multiply the dt. And then say we're going to start at time 0. We want to find how long it takes. And then Q is going to start at no transfer, and then the final amount that we need is this value here. I guess I'll just call this Q final, maybe. Q fusion. It's the Q to melt the ice. So this is an easy integral. Basically, you just need an amount QF. And then this side's really easy. It's 8.5 time. So the time just works out being the amount of thermal energy you need divided by the constant 8.5 watts of flow. And that works out to 10, and this is joules per second, and this is joules. So you get an answer that's actually in seconds, but then to make it more easy to understand, I converted it to hours, and the answer works out to be 10 hours, which is pretty reasonable for coolers. You know, if you go camping, you can throw a hunk of ice in there in the morning, and it'll still be there at night. I'll put the units here because that's kind of messy. Clean that up a bit. All right, so there we go. That is a Fourier's law calculation, and we get a reasonable result out of that. Now that was made easy by the fact that the temperature difference was constant. If the temperature difference is changing, then, well, the integral isn't quite so trivial to do. So now, now let's say the ice has been melted. How long does it take it to warm up to 10 degrees? So we'll assume everything else is the same. We'll ignore the air in the cooler, because air has a pretty small specific heat capacity. And now we're dealing with some water in here, because the ice is already melted. And this water is going to be at a variable temperature that's going from 0 up to 10 degrees. So how does that change things? Well, we see that the temperature difference is now going to be 20 minus T. It's a variable now, because when the water is at temperature T, the difference is 20 minus T. So when we set up our Fourier's law calculation, A delta T over R. This was a constant value last time, and so everything was easy, but now it's going to be a variable, and we're going to have to be, well, we're going to have to use the tools of of calculus for this. So we're going to cross multiply the dt like we did before. So dq is going to be A over R. Those are still constants, times delta T times dt. So we know what we're going to substitute for delta T, but a little bit of dq now is not going to be melting the ice. Instead, it's going to be raising the temperature. So a little bit of q is going to take the water and it's going to raise it by a little bit of temperature dt. So now we get the following differential equation. So there's the temperature increase of the little bit of the water, the small temperature increase of the water on the inside, and that corresponds to the little bit of thermal energy that's transferred in time t. So this is time and this is temperature. So we're going to have to separate variables here and integrate this. So this is just a Cal 2 problem, but setting it up and getting this far requires some good understanding of the physics. Now, to separate the variables, you have to divide by 20 minus t. You can't expand this. The only way to actually integrate this is to treat 20 minus t as one unit and divide it down like that. And then we'll throw all the other constants over on the other side, and then we just have a very simple time integral to do. So we've separated the variables now, and now we can integrate. So we want to know how long this takes, so the final time is a variable. And we know the temperature is going from 0C up to 10C. So let's see how that long that takes. Well, this is a pretty easy integral. This is just minus ln 20 minus t, and then we've got to put in our limits. And this is a trivial integral, because it's just time from 0 to t, so t minus 0 is just t. All right, so on this side, we will reverse the limits, and that'll get rid of this minus sign. So it'll be ln 20 minus ln 10, or ln 20 over 10. And, well, I guess I'll cross multiply r. Let's clean that up a bit. That's not going off to a good start. So I'll cross multiply RMC over A, and then that will be the amount of time it takes to increase the water temperature inside the cooler by 10 degrees. So we're going to substitute then. We've got ln 2 multiplied by the thermal resistance, which is 1.27 meters squared Kelvin per watt. Then we've got the mass, well, it was 1 kilogram of ice and therefore 1 kilogram of water. The specific heat capacity, 4,186 joules per kilogram Kelvin. And then we've got to divide by the area. There were 6 faces. Each was 30 centimeters squared, so we worked out the area previously as 0.54 square meters. So let's just check that this is dimensionally correct. So we got meter squared cancels, Kelvin and Kelvin cancels, kilograms and kilograms. We have watts, and then we have joules, joules over joules per second gives seconds. So this is a correct unit, and it remains just to calculate that temperature. Okay, and so we get 68.23 seconds, or 1.89 hours. All right, so while this is going on, the temperature will be increasing. The increase in temperature is actually going to happen most quickly at the beginning because the temperature difference is biggest. But then as the temperature starts to approach the temperature of the outside, i.e. delta T gets smaller, then the change gets also smaller. And so you end up with this sort of behavior, where this is the temperature of the room, and then this is the temperature of the water on the inside. And you could solve this if you put in T here, and then you could work out temperature as a function of time, and you'd find it's an exponential function of this form. We're actually going to do an experiment in class where we set up a plywood box, and then we put a heat source inside it, and then we monitor the temperature of the inside of the box as a function of time. And we'll see that we get exactly that sort of behavior. So that'll be an in-class activity. Also in class, we're going to look at the second way by which thermal energy transferred, and that is convective energy transfer. And then there'll be a convection experiment, mini experiment that we do as well. And that'll be our next topic then. We'll have covered the